Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss simply and multiply connected region, Cauchy integral theorem, and some examples related to Cauchy's integral theorem. Let's begin. What is simply connected region? A connected region is said to be simply connected if all the interior points of a closed curve C drawn in that of given region, let us say that a given region, let D, are the points of the region D. Let I prefer here is a region, given domain region D. We say that is a simply connected if all the interior points of a closed curve C all the regions of the interior point which is the simply connected. So, a simply connected domain D in the complex plane is a domain such that every simple closed path within it encloses only points of that given domain D. In other words, we can say any simple closed curve which lies in that of given domain the simply connected region, the shape of in form of square or we form it as a circle, ellipse, are some example of simple connected domains. Multiple connected region is bounded by more than one curve. Here we prefer one curve, but here in case of multiply connected region it is more than one curve, and we can convert a multi connected region into a simply connected one by giving one or more curves. Here two curves, that is a doubly connected region, If we choose a curve like this, inside that there will be another two curves, so it is considered as triply connected region. And we can convert that multi connected region into simply connected one by giving one or more crosscuts. In case of doubly connected region, I prefer one cuts, and in case of triple connected region I prefer two cuts to convert it simply connected region. In case of double connected region, that is a double connected region referred as C1 and C2. Now I convert that doubly connected region to a simple connected region by taking crosscuts Here I prefer cross cuts. Like this, C1, that one is C2. Here is the generally cross cut is used to convert that doubly connected region into simply connected region. But when you take triply connected region, let that one is the C, here C1, C2. So we convert it as simple connected region. Here I prefer a cross cut like this. At that of case, again we prefer a cross cut. This is a cross cut, that is a cross cut. To convert that triply connected region to a simply connected one, just cross cut is made like this, just a small one is going, another one is coming, then it is converted into a simple one. In this way, we referred what is simply connected region and what is multiple connected region, and how we convert a multiple connected region into a simpler one. Next, Cauchy's integral theorem. Statement: if a complex function f of z, which is analytic, and its first order differentiation f dash z is continuous at all points in a simple connected domain, then that integral f of z dz over a closed curve C will be 0, where C is a simply closed curve in that of given domain. You have to prove that one. Let us see be a simple curve simple closed curve in a simply connected region, simply connected region, connected region, or we can say that is connected domain, and f of z is equal to u as a function of x y plus I v as a function of x y can be analytic function, be an analytic function. So, z is equal to x plus I y, which implies dz is equal to dx plus I dy. Then closed curve integration over that of simple closed curve C of the given function f of z dz is equal to closed curve integration over C. F of z values are putted as u x y plus I v x y, next dz as dx plus I dy. Now multiplying closed curve integration, that C u dx plus I u dy plus I v dx plus I square v dy, which is equal to closed curve integration over C u dx minus v dy plus I closed curve integration C v dx plus u dy. Let we prefer it as equation number 1. Now, if f of z is analytic and its first order differentiation as we prefer, that one is continuous and continuous. So, we convert that integration into the region integration by using Green's theorem, as f of z is analytic in the domain and f dash z is continuous the real and imaginary parts, continuous the real and imaginary part u x y plus u x y is the real part and imaginary part v x y, and their first order derivatives are continuous. So, we can use Green's theorem. From Green's theorem, if we take two function m x y and n x y, these two functions are continuously differentiable, functions in a region. Therefore, the closed curve integration m dx plus n dy according to Green's theorem, that is converted to that of given region del n by del x minus del m by del y dx dy. Therefore, now we have to apply the Green's theorem to that of equation number 1. So, equation 1 becomes C f of z dz is equal to that integral change according to Green's theorem. We convert it like this manner. It is written as the region integration over R, here minus del V by del X minus del U by del Y dx dy. Here m as u, n as minus b, plus I, again that integral change to that form in that of region R. Here there will be no such region I mentioned, so I just write the integral one. That region is not mentioned. That integral change to del u by del x minus del v by del y dx dy. Use Cauchy-Riemann condition as that given function is analytic, as equation number 2. Since f of z is analytic, the Cauchy-Riemann equations are satisfied. The CR equations are satisfied. So we write del u by del x is replaced as del v by del y, and del u by del y is replaced as minus del v by del x. Hence equation 2 becomes closed curve integration f of z dz is equal to, here in place of del u by del x I substitute that is del v by del y, that will be 0. Again here in place of del u by del y I substitute minus del v by del x, that is 0, again that term will be 0. So we have f of z dz will be 0, which one is proved. So the Cauchy's integral theorem is proved as f of z is analytic and it is continuous at all points in that of simple connected domain. In that of simple connected domain, the closed curve integration over that of function will be 0. Here see, we prefer a simple closed curve in that of domain. Next, we can extend that Cauchy integral theorem. Here we prefer that domain is simply connected and the function is analytic and its first order differentiation f dash z is continuous in that of given region, in that of given domain. So for multiply connected domain, how we use Cauchy's integral theorem? Generally we say it as Cauchy's integral theorem or Cauchy theorem. Cauchy theorem. Now we extend the Cauchy's theorem to multiple connected region. Extension of Cauchy's integral theorem for multiply connected regions. If f of z is analytic in a given region R between two simply closed curves C1 and C2, then the integrals closed curve integration f of z dz C1 is equal to f of z dz C2. these integrals are same. How you prove it? We prefer doubly connected region as C1 and C2. So we convert that doubly connected region into simply one by taking the cross cut. Here the cross cut is used. C1, C2, let that is AB and that will be CD. From this to that, let us prefer EF. AB, EF, it is very small, very closed path. Very small in the sense the distance in between this AB line and EF line. Now that doubly connected region is converted into simply connected one. Now we can easily use Cauchy's theorem here. In case of simply connected region, Cauchy's theorem is used. According to Cauchy's theorem, the closed curve integration f of z dz will be 0. Let us say that entire curve referred as C. Now it is the combination of C1, AB, C2, EF, that entire closed curve C. Here I use a convention as if I proceed in anti-clockwise direction, let I choose positive sign. When I prefer clockwise direction, I choose negative sign. Anyone can use by taking clockwise direction as positive sign, anti-clockwise direction as negative signs. This is just a convention. And inward I take positive, outward I take negative. So that integral change to, for anti-clockwise C1, that is C1, I prefer positive, f of z dz. AB I prefer positive, plus AB f of z dz plus C2, that is clockwise, so it will be negative C2 f of z dz. Outward EF negative EF f of z dz is equal to 0. Where integration over AB f of z dz is same as integration over EF f of z dz, as integration over AB f of z dz is same as negative of EF f of z dz. These two are cancelled with each other. We have C1 f of z dz minus C2 f of z dz is equal to 0, or C1 f of z dz is equal to C2 f of z dz. Which one is proved? That is the extension of Cauchy's theorem or Cauchy's integral theorem. Now we have prefer a multiple connected region. Similarly, Similarly, if we prefer a multiply connected region like you have a multiple connected region as C, there will be various types of curves named as let C1, C2, C3, C4 up to Cn, then these curves, this multiple connected region can be changed to simply connected one by taking the cross cuts. Here I use the cross cuts to convert that multiple connected region into simple connected one. Now we can use Cauchy's integral theorem. So the closed curve integration over C f of z dz. Next, here the curve minus closed curve integration over C1 f of z dz. Here minus closed curve integration over C2 f of z dz minus dot 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 up to closed curve integration over Cn f of z dz is equal to 0, or closed curve integration over C f of z dz is equal to C1 f of z dz plus C2 f of z dz plus dot 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 up to Cn f of z dz. That is the extension of Cauchy's integral theorem. We prove it for doubly connected region. Similar pattern for multiple connected region. That formula holds good. Now we can solve a question by using Cauchy's integral theorem. A question in front of your screen. Evaluate the closed curve integration over C z square minus z plus 1 divided by z minus 2 dz, where C is a circle and equation of the circle is given. Equation of circle: magnitude of z is equal to 1. Magnitude of z, that is x square plus y square under root, is equal to 1. Taking square both sides, x square plus y square is equal to 1 square. Therefore x minus 0 square plus y minus 0 square 1 square. That is the equation of a circle. The circle, therefore the circle having origin at 0 0, the origin at center at origin, center at origin 0 0, and radius is equal to 1. So I draw a circle x o y x dash y dash 1 2 minus 1 minus 2 1 2 minus 1 minus 2. The circle of unit radius is drawn. Look at that given function z square minus z plus 1 divided z minus 2. So at z is equal to 2, here f of z that is z square minus z plus 1 divided by z minus 2 is not analytic at z is equal to 2, and z is equal to 2 is the point outside of that of circle. That point is outside of the circle. Therefore, by using Cauchy's integral theorem, the closed curve integration over C z square minus z plus 1 divided by z minus 2 dz will be 0, as there will be no such point inside that of given equation of the circle. In this way, we apply Cauchy's integral theorem to evaluate that given integration, given complex integration. With the help of this video lecture, you understand the idea of simple and multiple connected region, and how to convert a multiple connected region into simple connected region by taking some course. Cauchy integral theorem or Cauchy's theorem, the statement and proof of Cauchy's theorem, and we extend that Cauchy's theorem for multiple connected regions, the extension of Cauchy's theorem into multiple connected regions, and a question by applying Cauchy's integral theorem we solve a complex integral. So, with this useful and informative notes, let me wind up this session. Thank you.